That's right. Let's get our title straight. So I'd like to thank Professor Dunn for inviting us here today to talk about astronomical themes.
Okay, ask him to stop recording.
Too loud for you in the back? Is that okay? Too loud? Okay. Well, I'm going with it. So we're gonna talk about a few astronomy related things from Georgia State, and also we have one of your own here as well speaking. So let's get into it. What I'm going to talk about are supermassive black holes, not your ordinary boring black holes that come about when very hot blue stars die in their lives as supernovae and become black holes. The ordinary black holes tend to be only, a few solar masses worth of material. So we measure things by the mass of the sun. An ordinary black hole typically have anywhere from 3 to 10 solar masses worth of stuff. But on the other hand, we have supermassive black holes, and those things tend to be located in the centers of galaxies, as you see here. I'm going to walk around a little bit. So in the center of this spiral galaxy, one which is very much like our own Milky Way is also a spiral. And in fact, if this were our galaxy, we'd be about 2/3 of the way out from the center, about 25,000 light years from the center. But we can't see our Milky Way like this one because we're inside. So we can't see the forest or the trees. But inside this particular galaxy, which is known as NGC 1068, just a number, there is a very active supermassive black hole. And so if you zoom in, on this scale, this is on the order of thousands of light years across. Okay, so if you're on one end of this galaxy and you tell your buddy to fly to the other end of the galaxy, and then you turn your flashlight on, it's going to take thousands of years for the signal to reach your friend. But if we zoom in to this rather ordinary spiral galaxy, we can see this really bright region, and it's essentially ionized gas. This is gas that's fluorescing. What's happening is that very strong ultraviolet and X-ray radiation are stripping the electrons off of this gas. And when the electrons combine back onto the atoms, they give these very pretty colors. So the red here, you can see that sort of reddish purple. That comes from hydrogen, the simplest element in the universe. And it's basically, I don't know if you can see this, but it's in sort of a spiral shape here. And the spiral shape is outlining locations of hot blue stars, fairly young stars that have been born fairly recently, only within the last few million years. And remember, our sun is 5 billion years old. And the stars are ionizing the gas around it and causing the gas to fluoresce. And so the red stuff that you see is just due to star formation in this galaxy. But you also see this green stuff here, and the green emission is coming from oxygen. And this is oxygen where we call it doubly ionized because there's been enough UV and X-ray radiation to pull 2 electrons off of the oxygen atom. And when it starts to emit, gives off this characteristic green color. So you don't normally see this in most nearby galaxies, but you do in this one, and that's because it has a hidden supermassive black hole. Now these days, most supermassive black holes, the mass is on the order of about 1 million to 1 billion times out of the sun. So that's a lot, but it's still a small fraction of an entire galaxy. An entire galaxy may have 1,000 times more mass than that. So we're talking about 1 billion or 10 billion solar masses for an entire galaxy of stars. But still, 10 million is a lot of mass to squeeze into a region which is only about the size of the solar. That's a supermassive black hole. And these are the kind of black holes that you think about when you think about event horizons, where all the material has been collapsed down to an infinitely small point. And it's infinitely dense. And we can't see that at all, of course, because any light that enters into the vicinity of a black hole can't come back out, so it disappears. So you may ask, well, how do we know that they're there? And this is one reason, one way to know that they're there. So this has a supermassive black hole, and it's an active one, and so we call this an active galactic nucleus. So in general, active galactic nuclei live in the centers of some galaxies, and they are supermassive black holes that are accreting material. So you can see here, for example, in this artist conception, this is a supermassive black hole. It's just an artist conception because it's such a small area in the sky, we can't see it for now, at least. We're trying to build bigger and bigger telescopes to see these things. But it has this big porous of material surrounding it, which eventually becomes what we call an accretion disk of material. And it's just gas and dust being drawn in from the galaxy into the vicinity of the black hole. And as it spirals around, trying to enter the event horizon of the black hole, it collides with itself and heats up. So this gas is releasing this due to gravitational energy, which is making this gas come in, heating up, converting to kinetic energy, and then eventually to radiation energy as this gas heats up. And some of the radiation that comes out is in the form of X-rays or ultraviolet light. Remember, those are wavelengths of light, which are very short. We'll talk about wavelengths in just a minute. But if you're familiar with X-ray and UV radiation, you know that it's very high-energy radiation, and it strips oxygen of a couple of atoms as well as other elements, and causes it to glow. So that's what we think is going on here. Now, this particular supermassive black hole in this galaxy is hidden because we're viewing it from edge on. So all the material which is spiraling into the black hole is blocking our direct view. In other galaxies, we're seeing the more face on, and we can actually see a very bright point of light where the black hole is. So it's a little bit unusual. You think of a black hole as being something where no light can escape, and that's true. But outside the event horizon, where all this material is going in, it heats up tremendously, and they turn out to be the most luminous objects in the universe. So I study active galactic nuclei, those black holes that are active, that are actually feeding. So that hence the title of the talk. Black holes that are feeding and give back to their environment, which we call feedback. So the feeding part is matter spiraling into the black hole, and the feedback is this radiation coming out of the vicinity of the black hole and heating up the gas around it. So that's what we're going to talk about. We're going to talk about black holes that feed. And we'll see if they're methane eaters. Okay, so what proof do we have that supermassive black holes actually exist? We've known about black holes for quite a long time now, but they started out as just an idea. And eventually you have to prove your idea. You have a hypothesis, you've got to go out and prove it. And in this case, we're talking about a supermassive black hole that was discovered in the middle of our own galaxy, in the middle of the Milky Way. So, you go out at night, look at the night sky. Well, if you do it in downtown Atlanta where we are, you won't see anything, right? There might be a few bright stars. But if you go out into the country, and particularly in the summer, you see this big band of light stretching out over your head. What is that? The Milky Way. It's our own galaxy, which again we can't see too well because we're inside of it. But in the Milky Way, toward the constellation of Sagittarius, and if you're familiar with constellations at all, which astronomers don't really do too much of, we leave that for the astrologers, but and there's a teapot, which we call Sagittarius, looks like a teapot in the sky, and near that teapot is actually the center of the galaxy. So we know where the center of the galaxy is. And we can't see it in visible light, so we have to go to other wavelengths in order to see the center of the galaxy. It turns out that you can see the center of the galaxy in the infrared. So using infrared light or radio waves is another way to do it. But in this case, infrared light, we can actually see the center of the galaxy. And so people have actually been looking at the stars in the middle of the Milky Way. And remember, this is about 25, so the entire galaxy is about 100,000 light years across, so it's about 25,000 light years away from us. And we're looking at something which is only about 10 light days across. So we have these very large telescopes now that allow us to see very fine details and actually pick up stars in the middle of the Milky Way. And when you do that, and you follow it over the course of about 14 years, you start orbiting something in the middle. So look at the red cross there. Then we're going to run this little movie. So these are actual observations. We're going to zoom in and look at the center of the galaxy. Well, there's a red cross there, but in reality, you don't see it. Okay? And so what's there is a supermassive black hole. And I don't know how many of you had astronomy, but if you have, you certainly heard of Kepler's law, right? So Kepler's third law allows you to actually measure the mass of this unseen object in the middle of the galaxy by following the orbits of these stars. And when you measure the mass, it turns out that there's the mass there that we don't see is about 3 trillion solar masses. So we know that there is a supermassive black hole in the center of our galaxy, but it's not an active black hole. It's not sucking in material and letting off a lot of radiation. It's probably fortunate for us that it's not, although I think we're pretty well protected from being in the galaxy and having all the stuff and gases from it. But you certainly don't want to be near an active supermassive black hole when it ignites.
No, the Brooklyn Art Fair.
Okay. Well, we're going to take a little aside and go back in time a bit, give you a little history lesson. So back in 1963, an astronomer actually made the cover of Time magazine, which is an unusual event in and of itself. And this astronomer name was Martin Schmidt from Caltech. And what Martin Schmidt did was basically discover that these quasi-stellar radio forces, which we now call quasars, are all at very large distances. And yet they put out a tremendous amount of light, and they're very small. They don't look like galaxies or other big blobs of material. They sort of look like stars, and hence the name quasi-stellar. And people have been studying these quasars that were originally discovered from radio surveys and wondering what they were, and so they started taking spectra of these quasars. How many people in the room know what a spectrum is? Show of hands here. All right, so you know what a spectrum is. Basically, you take light and you spread it out to its constituent colors or wavelengths. Okay? And they were puzzled because the emission lines they saw, these are just radiation at specific wavelengths due to electrons jumping around in atoms. He was puzzled because the emission lines that they saw, which is up here in this very old-timey spectrogram, they didn't match any elements that we knew about here on the Earth, and that was very puzzling. Until he realized that this spectrum of this object, in this case the quasar 3C273, was actually redshifted. Okay, so how many people here know about redshifts? Raise your hand. Okay, all right. You know that when you see something that's redshifted, what is that object doing? It's moving away from you. And the greater the redshift, right, the faster it's moving away. It doesn't depend on how close the object is. It can be any distance from you.
31. It's about halfway through.
No, I recognize.
So that just came about and led us to the expansion of the universe at this time. But they didn't realize that quasars were part of this expansion and at large distances until Martin Schmidt came along. So Martin Schmidt came along and he discovered that quasars are at large distances, but yet we can still see them, so they must be very luminous. But they're also very point-like. You get a tremendous amount of energy coming out of a very small volume of space. And this was a big puzzle. Later, we put these quasars into a bigger class of objects called active galactic nuclei, which is what I studied. And we eventually realized that these were supermassive black holes that were drawing in gas and dust, heating up, and spewing out radiation. So as I said before, these are very messy eaters. And you try to feed them a bunch of gas and dust. Some of it goes into the event horizon. Some of it gets blown out. Okay? If you ever had children, you know what this is all about. Okay. All right, now we're going to segue to a commercial. I am the chair of the Department of Physics and Astronomy at Georgia State, and you will be part of us very shortly. So I thought I'd tell you a little bit about the physics and astronomy we do at GSU. And this sort of will lead back into the study of black holes and galaxies. So we do have an undergrad and an undergrad program there. It is physics and astronomy. We do extragalactic astronomy. So you can see here we have 3 astronomers doing that. We have 5 astronomers doing stellar astronomy. And you will hear from some of these. These are faculty members you hear from a postdoc and a grad student doing stellar astronomy. And lately we've added on solar physics as well. So we're having people doing that. And we have all these nice resources that we can use. So if you've heard of the Chara Array, this is actually a Georgia State facility out on top of Mount Wilson, which is right next to Pasadena, California. So if you go on top of this mountain, you look out over the Los Angeles basin, you wonder why we would ever put an observatory there, because there's just light everywhere. But it turns out that we're above a lot of the lights in the clouds. And in fact, sometimes clouds will come in and cover the Los Angeles basin. Still observed. So the Chara Array is actually 6 telescopes combining the light together to allow us to see very fine details. It's the largest interferometric array that uses optical and infrared radiation in the world. We're also partners, and I'll come back to this in a minute when we talk about my science, with a 3.5 meter telescope. So that's sort of an average medium-sized telescope these days out at New Mexico. We have a lot of collaboration and actually a part of a consortium down in Chile. So some of our grad students and undergrad students go down to Chile to observe. And then we have Harley's Creek Observatory. Anybody here ever been to Harley's Creek? Okay, 50 miles out on I-20 East, we have an observatory with a couple of telescopes, and I understand you've got one here. I saw it coming in. You can also go out there if you like, 50 miles east near Rutledge, Georgia. We have a 24 and a 20-inch telescope. Okay, so let me tie this back in. Oh, one more thing I wanted to mention is you can get your bachelor's in physics at Georgia State and substitute a few advanced astronomy, astrophysics courses to get an astronomy concentration. Now let's go back. We're ending the commercial and going back to linking what we do here in terms of extragalactic astronomy with what I study. I will point out that both myself and Dr. Bent study supermassive black holes. We think that's cool. It turns out that Dr. Rachel Cugneri studies an even more mysterious thing, which we call dark matter. Black holes are actually not dark matter. Black holes could be just ordinary matter that collapses down to an infinitely small state. Dark matter is something that we know nothing about, almost nothing about. We can see its gravitational influence on galaxies around us, but we don't know what it's made up of. All right, so what do I do? Well, we're looking at the monster. We're looking at the monster, the supermassive black hole in the center of just about every galaxy. And we're not looking at the ones that are not very active. In fact, only a few percent of galaxies these days have active black holes. So we're looking at these active black holes, and we're using various tools to do that. One tool is the Gemini North Telescope on top of Mauna Kea in Hawaii. Unfortunately, we don't usually get to go there to do our observations. We do it remotely, darn it. But I have been, and if you go observing on Mauna Kea, you need to take a couple of things. You got to take your swimsuit, and you got to take your heavy coat. Okay? You want to take your swimsuit because you go snorkeling on the beaches there. You got to take your heavy coat because it's very high altitude. Experience extreme. Turns out that Mauna Kea is one of the best sites in the world for astronomy. The atmosphere is very steady. You're above most of the water vapor, and taking your telescope, the Gemini North called Gemini because there's a twin telescope down in Chile.
No! I want
So we use Gemini North. This is actually a laser beam coming out. Normally you think of just receiving the light here in Astronomer. This is a laser beam coming out of the telescope. The reason for that is because it creates an artificial star in the sky that we can use to guide on as objects move across the sky. So we're creating our own artificial stars, bright things that we can guide on while we're looking at the So what we do with this telescope in terms of feeding them on to the black hole that's in the center of galaxies is we get these big data cubes. And if you're familiar with a spectrum, this is one more step beyond that. Because now we can get a spectrum, we can get an image, and at each point in the image we get a spectrum. So this is like a 3D data cube where X and Y represent coordinates on an image, and then if you go that way, you actually get a spectrum. So using this new technology, we're able to get pictures at various wavelengths, for example. So here's one. Here's Markarian 509, another active galactic nucleus. This is a starburst ring surrounding this very bright ACN that's in the middle there, that's feeding. And we discovered this sort of thing here, which I'm going to call, hopefully nobody is in here for copywriting purposes, I'm going to call a swoosh, a Nike swoosh, or a check mark if you want to call it that. So we discovered this swoosh here and wondered what it was. We went back and looked at this data and produced what we call velocity maps. What's a velocity map? It's basically a map of blue shifts and red shifts. So if you look at this same region here now, this represents the galaxy down here in the lower left-hand corner, and you see blue shifts on one side and red shifts on the other. So what's the galaxy? It's rotating, right? So this part is coming towards you on the left side, and on the right side is going away from you. So galaxies rotating like galaxies do, but when you subtract off the rotation, you see another part which is blue shifted, and then slightly red shifted as it makes this turn. So it comes down, makes a turn into the galaxy, and it's red shifted. What we think is going on here is that gas coming from behind the galaxy, because remember, this is actually a 3D universe, not 2D. So it's coming down from behind the galaxy, hitting the galactic plane, and then being diverted down into the center. So it's blue shifted as it comes towards you, hits the galactic plane, and then red shifted as it goes down into the nucleus. So we think this is actually one Well, we talked about feeding it, but we have to look at what comes out. And so for that, we've been using Hubble Space Telescope for quite a long time now. Everybody knows what Hubble is, right? Been up there for more than a couple of decades. The advantage of Hubble Space Telescope is that it allows you to see very fine detail because you don't have the distortions in the atmosphere. And Hubble has the imaging capabilities. This image came from Hubble, and again, it's just ionized gas coming out from the central supermassive black hole. But it also can take spectra. So in this case, we obtain spectra all along this split location here. And when we analyzed the spectra and then tried to understand what the velocities again were telling us, again, blue shifts and red shifts, came up with this model where this part down here, this is astronomy, right? So actually, you look at this on this image, east is to the left, north is up. So in the southwest here, in the lower right-hand corner, this stuff is blue shifted. In the upper left-hand corner, the other stuff is red shifted. Okay. So what we're seeing here is evidence for feedback. In other words, material being blown out of the center of the galaxy, supermassive black hole. So they're messy. Well, this is really complicated. And so since I'm doing this work with your professor, Jay Dunn, you're going to ask him questions about that because it's too much for me to explain. So this is a homework assignment for you. Ask Jay. Where are you, Jay? Yes. Sometimes you explain this to them because it's basically telling us that we can see outflows in ultraviolet as well from absorption filters. They're all blue shifted. And so with that, I'm going to leave the hard stuff to Jay. You're welcome. By the way, if you didn't catch it, Jay was actually my student, now my colleague. So we still work together. Well, so far I've talked about feeding the black hole, and I've talked about feedback from the black hole. But the last thing I want to talk about is what happens to that feedback when it hits the rest of the galaxy. Because it turns out in astronomy, we've discovered in the last 10 years that there is a very close relationship between the black hole in the middle, remember about a million to a billion solar masses, and the galaxy around it, which is 100 or 1,000 times that mass. It has on the order of 10 or 100 billion stars. There's a strong connection. And what we found is that the mass of the black hole is very strongly linked to the mass of the whole galaxy. And we've been trying to understand that for 10 years, not really understanding why. Because the black hole itself should only control the inner few light years around it, and yet somehow it knows about the rest of the galaxy spanning hundreds of thousands of light years. So one thing we've been doing, we don't have an answer yet, but I'm telling you how we're going to get there. One thing we've been doing is using our partnership out in New Mexico with this 3.5-meter telescope and taking images and spectra of the entire galaxy itself and then relating that to what we see on much smaller scales with Hubble and with the Gemini telescope. And so we just started doing this over the last year. This is a really nice facility because if you're a student, whether you're an undergrad or a grad student, we've taken both out there, you basically have to go out here in New Mexico and spend 3 nights learning how everything works. And then after that, you sit at home with your laptop and run the telescope that way. So you lose some of the drama, but you don't have to keep traveling back and forth to Mexico. So, in fact, I turned this entire project over to an undergrad physics major, a very, very good one, who's concentrating in astronomy, Camilo Chuka. So Camilo's been taking spectra of the entire galaxy, and you can see some spiral arms here for this galaxy, and trying to match up the outer parts and the inner parts. And what he finds is that the central AGN, the supermassive black hole that's active, is ionizing these spiral arms, stripping electrons off of the atoms, and pushing material away from the galaxy itself. And so, in fact, to make this little plot here, it's kind of hard to see, but on the left-hand side, things are blue-shifted. On the right-hand side, they're red-shifted, so this is rotation again. But when you get into the middle, it reverses itself, which you wouldn't normally see, and that's from the outflow itself. And so what he's finding is that these central black holes are actually blowing gas out of the galaxy and stopping star formation going on in the galaxy. So there's some link between how galaxies grow by star formation and how black holes grow by feeding and then feedback. And we still don't know what the answer is, but that's part of the fun of it. So I'm just going to look to the future now. What's the future particularly for me, for my colleagues, but also the future for most astronomers? And that's the James Webb Space Telescope. Who's heard of this one? Okay? It's the next Hubble, essentially. Many times bigger than Hubble. And it will be launched, they say, NASA says, in 2018, so just a few years from now. It's a structure that actually unfolds. You can't make a mirror that's this big and launch it into space. It's made of segments, as you can see here, hexagonal segments. And so it will unfold, and it will allow us to peer much deeper and deeper into the universe. So you don't have the problems with the Earth's atmosphere, and you don't have problems with certain wavelengths that like to be blocked out, like ultraviolet light or infrared light. You can look directly. And the neat thing about this is that, as most of you know, as you look back into the universe, you look back in what? In time. Because it takes light a long time to travel from where it was to what you see. So as you look back into the universe, you're looking back in time. So now we can take our studies of nearby supermassive black holes and look back in time to see what they were doing when they were younger and trying to understand exactly how black holes and galaxies form together. So that's something exciting. hopefully we'll get some observing time here. You have to compete for it, but we're looking forward to those kind of studies in the future. And that's it. Thank you very much.